A graph traversal is a procedure for systematically going through all of a graph's vertices and edges. When you think of a graph, you may think of something like the graph shown here, which is about 7 vertices and 7 edges. And you may wonder, why do you need a formal procedure when it's obvious how many vertices and edges there are? But in many real-world applications, the graphs are much larger and look more like this. For example, a social network can be represented as a graph with people being the vertices and the connections between people as the edges. Such a graph will have millions of vertices and hundreds of millions of edges. So if we need to explore such a large graph, we would need to do this systematically with an algorithm. The first challenge when we traverse a graph is to make sure that we don't get stuck in a loop, because large graphs will likely have several loops. We also want to make sure that our algorithm is efficient in both running time and the space that's required. There are two main graph traversal algorithms. One is called depth-first search, and this algorithm visits child vertices before sibling vertices. This small graph illustrates this. Let us say I've already visited the two vertices shown in blue, and I'm currently at the second node. Depth-first search will choose to move towards a child node before moving to the sibling node. This is in contrast to the second approach called breadth-first search, where you visit the sibling vertices before the child vertex. The two algorithms are similar, but they use different data structures. Depth-first search uses a stack or is implemented as a recursive function, while breadth-first search is implemented with a queue data structure. In this presentation, we look at depth-first search. The approach is similar to exploring a maze. Imagine you are inside a maze and you can only see the corridors around your current location. So as you move through each intersection, corridor, or reach a dead end, you make a mark on the wall so that you don't get into a loop. And if you carry along a rope, then when you reach the end of the maze, you can find your way back to the entrance by following the rope. In our computer implementation, we will use a stack data structure as sort of like the rope. This is a pseudocode for the depth-first search algorithm. This particular implementation uses two data structures, a stack and a set, to store whether a vertex has been visited or not. Initially, all vertices are stored as not visited in the set, and we push the start vertex onto the stack. The algorithm then enters a loop that continues until the stack becomes empty. In every iteration of this loop, you pop the top vertex of the stack, and that becomes the current node. If that vertex is not visited, you mark it as visited and then push all of its neighboring vertices onto the stack. The algorithm will become clearer when we go over an example. But before that, you will notice that the for loop in the algorithm does not actually specify the order of adjacent vertices. The order does not matter, in the sense that any order will be a correct traversal. However, for consistency, if we want to get the same answer as everyone else, we have to make sure that we select vertices in some particular order. The alphabetical order of the vertex labels is one way of doing it. This is also called the lexicographic order. We'll follow this lexicographic order when we go through the next example. So here's the graph that we want to explore. I want to do a depth-first search starting from node A. Initially, all the vertices are marked as not visited, and I have my start vertex A pushed onto the stack. Now I'm ready to begin. At every iteration, I will pop the top of the stack, and that node becomes the current node. Current node A has 3 children, and we've pushed these children into the stack. Note that we push them in lexicographic or alphabetical order, so first C, then E, and H. After this, we are done with the current node A, so we'll mark A as visited, and then we'll pop the top of the stack, which is H, which becomes our current node. Notice that as I mark a node as visited, I also show that at the top of this slide so that you can see the sequence of visited vertices at the end of the algorithm. The arrow on the edge indicates the node from which we arrived at a node, that is its parent. Alright, now we will do another iteration. Vertex H has 2 neighbors other than its parent, so we push them onto the stack, again in alphabetical order, so F, then G. Then we are done with H, and we can mark H as visited. We'll then pop the top of the stack to identify a current node, and now we are at G. G only has one neighboring node, C, and we push that onto the stack. Okay. So we are done with G, so we'll mark G as visited and then pop the stack to give us the next current node, C. C has one other adjacent node, which is A, and we push A onto the stack. We are done with C, and we can mark it as visited. Okay. And now when we'll pop A, but when we reach A, we notice that A has already been visited. We can immediately move to the next iteration in this case. The edge between C and A that connects the current node with the node that was previously visited is called a back edge and indicates the presence of a loop. In fact, one of the applications of depth-first search is to detect loops in a graph. Okay. For the next iteration, we again pop the top of the stack, which gives us F as the current node. At F, we have one adjacent vertex E, so we push that onto the stack. Now we are done with this iteration, so we mark F as visited, pop the top of the stack to get E as the next current node. At E, we have two adjacent vertices, so we push them onto the stack, again in alphabetical order, so A, then D. As usual, we are done with E, and we'll mark E as visited and pop the top of the stack to get the next current node, which is D. D has no other adjacent vertices, so we are done with D. We just need to mark D as visited and pop the top of the stack to get the next current node, which is A. Note that we have already visited A previously, so there is nothing to be done here. Edge E to A is a back edge. Okay. Well, we pop the stack to get the next current node, which is E. E has been visited previously, so we can immediately move on. We pop the stack to get the next current vertex, C. C has also been visited, so we pop the stack, and that leaves the stack empty. The condition for us to exit the algorithm. Note that I've listed the order in which I marked the vertices, in which I've mark the vertices as visited at the top, and you can check that I visited every vertex in this graph. Next, let's look at the complexity of the running time of depth-first search. Here, V represents the total number of vertices and E the total number of edges in the graph. So these numbers are a measure of the size of the graph. And let's also assume that changing the label of a vertex from visited to non-visited takes a constant amount of time, that is O of 1. Notice that each vertex is labeled twice. Initially, all vertices are marked as not visited, and then over the course of the algorithm, the vertices become visited one by one. So the total cost of this step is O of V. Now in every iteration, we also push all the adjacent vertices of a vertex to the stack. The number of adjacent vertices or edges is called the degree of a vertex. There is a theorem about graphs which says that the sum of the degrees of all vertices in a graph is twice the total number of edges. So we can use this result to say that the total time taken to complete the for loop is O of E. And that means that the total time to run this algorithm is O of V plus E, which means that the running time of this depth-first search is proportional to both the number of vertices and edges in a graph. By the way, this assumes that the graph is represented as an adjacency list, which ensures that we are actually able to get all the adjacent vertices in time proportional to the degree of the vertex. Not all graph representations are capable of doing this. The space complexity of this implementation is O of V, mainly because the set data structure needs to store whether every vertex is visited or not. In practice, this space requirement is a serious limitation when searching very large graphs. So there are variants of depth-first search that do not store whether every vertex is visited or not. There is another way of implementing depth-first search that uses recursion, and it does not use a stack data structure. The pseudocode of the recursive implementation is shown here. But there is still a hidden stack in this algorithm. Can you see where it is? It is the call stack of the recursive function itself. The main advantage of this implementation is that, as you can see, it's much shorter and simpler than pushing and popping from a stack data structure. However, the recursive function is more likely to suffer from a stack overflow error because you'll typically have a very deep call stack, one that is as big as the number of vertices and edges in the graph. So it is less practical to use a recursive implementation to search a large graph.